welcome back. So in this lecture we will discuss about shear force and bending moment diagrams particular to the simply supported beams. We shall discuss two cases. One is a point load acting at an offset of the midpoint, and other is uniformly distributed load over the simply supported beams. So let us see the first case where we have a simply supported beam carrying a concentrated load at which is not at the midspan. So A and the beam is supported at A and B. The point load is acting at point C, which is at a distance of A units from support A and B units from the support B. The overall length of the beam is capital L. Okay, so the magnitude of the load is capital W. So what we do in case of simply supported beams, it becomes mandatory to evaluate the reactions, right? So in this case, if we evaluate the reactions first, we know that RA plus RB is equal to W, and we also know that sigma MA must be equal to 0. So if I apply this identity sigma MA equal to 0, I get RB multiplied by L minus W times A equals to 0. That gives me RB equal to WA by L. And at the same time I get RA equal to WB by L. So once we get these reactions, now it is up to us that from which point we want to take it as a reference point. For example, in cantilever beam we could take the free end as a reference point and things become slightly easy as far as the calculations are concerned. But in case of simply supported beams, you can choose either support A or support B as a reference point. So here let us say we choose a support B as a reference point. So we take a section at a distance x from point B. So since between B and C the loading does not change, we take section left of B to evaluate the shear force. So the shear force to the left of section B becomes, so if I draw this section here, shear force become minus of RB, and RB is equal to W times A by L, and since it is to the right of section and upward, we have a minus sign here, right? Same way we can take a section right of A, the another section is here. So when we take this section right of A, so the support is here, section is here. So this is WB by L. So the shear force is now to the left of section and upward. So shear force will be positive now. That is WB by L. This is for section AC. This is for section AC. This is for section BC. B to C. Right? So once you take this shear force, now the question arises for the bending moment. Now the bending moment is, in this case the distance is x units. So the bending moment will be force multiplied by distance, that is WA by L multiplied by x. So WA by L multiplied by x, that is bending moment. Now x is varying from 0 to B in this case. Okay. For this section AC, your x is being taken from the support A, so therefore the moment will be WB by L is force, perpendicular distance is x, so this is WBX by L. Now here the x is changing from 0 to A, sorry. Please note this thing. We are not keeping the reference point as same for both the sections. For first section BC we are taking B as a reference point. For section AC we are choosing A as a reference point. So this is very clear when I write this x is changing from 0 to A here, x is changing from 0 to B. Okay, and point C correspond to x is equal to A in the second equation. Let us say I call this equation as 2 and I call this equation as 1. So point x is equal to B correspond to the bending moment at point C. So that is WAB by L. So I get the bending moment at point C is equal to WAB by L from both the equation. Right. So the next task is to evaluate the shear force and bending moment diagrams. So please make sure that we get these equations for shear force and bending moment diagrams, bending moment equations very accurately. So once we have obtained the shear force and bending moment expressions for both the section, we can draw the diagrams. So let us say we try to draw the shear force diagram over the span. So let us say we have this point as the point C. So let us say we have obtained these equations for shear force and bending moment diagrams. So we need to plot them for the shear force and bending moment diagrams. So at point B, the shear force is WA by L and that is negative. So let us say I mark this point as WA by L towards the downward side of the reference in order to show that it is negative. And at till point C, the shear force remains constant. At point C, the shear force becomes plus BWB by L. So that means plus WB by L. And in between A and C, this remains constant. So this zone is a positive zone. So this magnitude will come out to be WB by L. So this will be my shear force diagram. Note that from geometry it is very clear that A is greater than B. Therefore I have clearly shown that WA by L is greater than WB by L. Next, when we move to bending moment diagram, for bending moment diagram, we can clearly note that the bending moment at point C, at point B and at point A is 0. Bending moment is 0 at x is equal to 0. At x is equal to 0, bending moment is 0. In this expression also, at x is equal to 0, bending moment is equal to 0. So in second equation, x is equal to 0 correspond to point A, and in this equation x is equal to 0 correspond to point B, right? So what is the bending moment at point C? We know that it is equal to WAB by L. So this is somewhere WAB over L. Now in between C to A and in between C to B, the equation is a linear equation, linear in x. So therefore joining this with the help of a straight line will be a right mathematical representation for the distribution between C to A and C to B. And since both of these expressions are positive, we have drawn this over the reference line. So this will be my bending moment diagram. So this is shear force diagram, SFD, and this is bending moment diagram. We can also note few observations here. One is the shear force diagram is constant, distribution is constant between B to C and C to A, because there is no shear force between B to C and C to A. There is no vertical force, you can say. At point C, there is a sudden jump, okay, and this sudden jump, the extent of the sudden jump is equal to the magnitude of point load applied at point C. So whenever you have a point load in the beam, there will be a sudden jump in the shear force diagram, and the extent of the sudden jump will be equal to the magnitude of the point load, right? Now if we compare shear force diagram and bending moment diagram, the degree of bending moment curve is one higher than the shear force curve. You can see that shear force is constant in this zone, while the bending moment is linear in this zone. You can see that shear force is constant in the zone CB. In the same zone CB, the bending moment is linear. So that means the bending moment is always 1 degree higher than the shear force curve. Another thing you can note that the maximum value of bending moment arises only when the shear force vanishes. Okay, so it means that maximum bending moment correspond to the zero shear force. So these are few observations which you can note it down for your further references. Okay, if this is clear, we can definitely move to our next example, wherein we look at the uniformly distributed load applied at a simply supported beam, right? So let us say we have a simply supported beam which is supported at points A and B, okay, and the intensity of load is W per unit length, total span is L, center is, let us say, C. Again, the first of all we try to evaluate what is the amount of reactions at A and B. So RA and RB reactions here will be equal and will be nothing but half of the total load. So total load is W times L, so the reactions will be WL by 2. Now since in between A and B you do not see any variation, there is a load applied continuously but there is no change you can observe, so only one section is sufficient. So we take a section at a distance x from here. Okay, so once you take this section, the free body diagram of the section is like this. This is W L by 2 and this distance is x. So my shear force will become WL by 2 vertical, so it is minus WL by 2 plus WX. So this is a shear force expression. Same way for the bending moment, what will happen? This is WL by 2 multiplied by X minus, so for bending moment I'll write it here again so that you can see the calculation. So WL by 2 multiplied by X, and since it is in anti-clockwise direction to the right, so it is treated positive. Now because of WX, because of small w, this may be assumed to act through its CG. So W into X is the intensity and the perpendicular distance is X by 2, so that makes it minus WX square by 2, and these two expressions are valid for X greater than 0 and less than L, so means over the whole span. Sometimes it becomes important to see where the bending moment is maximum. So bending moment will be maximum where its derivative will be 0. Okay, so to obtain the value of maximum bending moment where the derivative of bending moment is 0, so we differentiate bending moment with respect to X, so that becomes WL by 2 minus 2WX by 2, that is WX. So X is equal to L by 2. It means that at mid span the bending moment is maximum. Till now we are able to obtain the location of the maximum bending moment. We did not obtain what is the amount of the maximum bending moment. So location of maximum bending moment is X is equal to L by 2. So and the magnitude of maximum bending moment will become after you substitute X is equal to L by 2 in the bending moment equation. So once you substitute that, the maximum value value of bending moment will be WL square by 8, and it will occur at mid-span, that it at x is equal to L by 2. So these are few points which you can note while plotting the shear force and bending moment diagram. So let us have a look how we are going to plot them. Please note that the variation of shear force is linear in x, so it will be follow a linear law. Bending moment is a quadratic in x, so it will follow a parabolic law. So let us see how we are going to draw them. So once we have obtained the expression for shear force and bending moment diagram, once we have obtained the expression for shear force and bending moment calculations, and we know that these equations are valid for the whole beam, that is ranging from x is equal to 0 to L. So we can calculate for the shear force and bending moment at specific points. For example, the shear force at point B correspond to the shear force corresponding to x is equal to 0, which will give me minus WL by 2. Okay, same way you can calculate for shear force at point A, which will be shear force at point x is equal to L. If you do the calculation, you will get it as plus WL by 2. Right now, it is wise to get the shear force at some other point, say the midpoint. So let us say shear force at point C, which is corresponding to x is equal to L by 2. So once you put x is equal to L by 2, I get shear force equal to 0. So once you obtain these values of shear force at point B, A and C, you can plot them on a curve. So what is the value of shear force at point B? It is minus WL by 2. Let us say it is somewhere here. So minus WL by 2, and at point C it is 0. So here, and at point A it is again plus WL by 2. So let us say somewhere here. Now to join these points, you have to use the equation of a straight line. So therefore we join them with the help of a straight line, which will pass through the point C. So this is a positive zone, this is a negative. So in order to draw the bending moment diagram, we look at this equation now. Same way we evaluate the bending moment at point B. Bending moment at point B means x is equal to 0. So once I put x is equal to 0, bending moment is 0. At point bending moment at point A means x is equal to L. When I substitute x is equal to L, the bending moment is again 0, and it must be 0. So if I do the calculation for bending moment at point C means x is equal to L by 2. That means it will come out to be WL square by 8. So WL square by 8. So what we can do is simply bending moment at B is 0, bending moment at A is 0, bending moment at C is WL square by 8. So this is the bending moment. So when you join the bending moment points at A, B, C, make sure that you follow the path of a second degree curve, since the bending moment equation is a second degree. So you make a parabola here. Okay, so this is it. Please make sure that you draw a parabolic curve here. Parabolic curve. So this will be a bending moment diagram, obviously all positive, since through calculations we have obtained the same. So this will be our shear force and bending moment diagram for a uniform loaded beam, simply supported at both the ends. So thank you very much.